Hello, I want to talk today about electrocyclic reactions. We mentioned these briefly in class yesterday, but I want to give you a little longer overview and talk about how we're going to analyze these reactions using molecular orbital theory. All right, so what I have up on the board, just a couple of notes. Right, when we talk about electrocyclic reactions, we're going to focus exclusively on the HOMO, the highest occupied molecular orbital. These reactions, unlike cycloadditions, all electrocyclic reactions are intramolecular. You're dealing with a conjugated pi system, and it must be all within the same molecule. They can be ring closing or ring opening, right? We're going to go in the ring closing direction, but you can also open up systems, and we'll see those in applications that you're going to do for homework, right? So these reactions that we want to explain are ones like the one up here, where we have hexatriene, and that's reacting to form cyclohexadiene, either with the methyl group cis or the methyl groups trans, right? And the really interesting thing about these reactions is that depending on whether you heat them or you shine light on them, you get a different outcome. When we heat it, we get this achiral material. When we shine light on it, we get this chiral material. And again, to be clear, we're also going to get the enantiomer of that molecule, right? And like we said in class, the way that we can understand what's happening in these reactions is to look at the molecular orbitals, right? And that's what we're going to have to do. So the first thing for us to do is to generate a molecular orbital picture for a 6p orbital system, right? So we're going to look at this molecule, right, the reactant, and see if we can figure out what the molecular orbital picture will look like, right? And if we think about that, we have a conjugated array of p orbitals where we have a p orbital at 6 consecutive carbons. So we're looking at a 6 pi orbital system, right? 6p orbital system, right? Where we're going to look at combining 6p orbitals to give us 6 molecular orbitals, right? And this is consistent with what we've done for ethylene, 2p orbitals, 2 pi molecular orbitals, butadiene, where we've seen 4p orbitals give you 4 molecular orbitals. Here, hexatriene, we're going to have 6p orbitals giving us 6 molecular orbitals, right? And the way to think about it, so we're going to start with 6p orbitals, right? Those are going to come in at whatever their energy is. And since it's an even atom system, we're going to get 3 bonding molecular orbitals, 3 anti-bonding molecular orbitals. Right, and we're going to have psi1, psi2, psi3, psi4 star, psi5 star, psi6 star. Okay, and we know that we have 3 pi bonds, so if we count the number of electrons in those pi orbitals, we're going to end up with 3 times 2, 6, right? So we have filled up the bonding molecular orbitals, right? And again, this is our ground state. Right? We also know that if we shine light on this, we're going to promote one of the electrons to the lowest anti-bonding orbital. Right? So we're going to look like that, right? And again, the key for us is to recognize what the HOMO is. So in the ground state, the HOMO is psi3, right? And in the excited state, the HOMO is going to be psi4 star. So when we're looking at the thermal reaction, right, the one that we have here, we're going to be looking at HOMO psi3, right? Because that's our ground state reaction, right? So it's important for us to remember this is going to be ground state. So HOMO is going to equal psi3, right? And when we do the photochemical reaction, that's going to be excited state. Right? And that's going to be HOMO psi4 star. Okay? So that's how we're going to look at this reaction. And now let's see if we can understand why we're getting the bond formation and stereochemistry that we get. All right. For me, all right, so let's do the thermal reaction here. For me, it's always easiest to orient these with the opening pointing down. So I'll draw it like this, right? And we have the methyl groups pointing out to the left and to the right. And we can draw in what the orbitals look like, right? And one thing that we can do is we can draw out all of the molecular orbitals if we want, or we can use some of the things we talked about in class to just draw out the orbital we care about. So if we're looking for psi3 as the HOMO, right, we know, so again, if we're just going to focus on psi3, right, we know that psi3 is going to have 2 nodes. Because again, the psi number -1 is the number of nodes. Psi1, 1 minus 1, no nodes. Right? Psi3, 3 minus 1, 2 nodes. And if we think about how to make 2 nodes symmetrical, hopefully it's clear we're going to have a node after the second p orbital and a node after the fourth, so that we end up with an orbital that looks like this, right, where we have 2 nodes and 3 areas of overlap. That would be our psi3, right? And now what we're trying to do is to figure out how to rotate. Do we take these and rotate them in, right? That would be disrotatory, they're rotating opposite directions, or rotate them that way, conrotatory in the same direction, right? And we're trying to get orbital overlap to form the new sigma bond. Okay, so if we look at this system and we rotate the first bond in a clockwise direction, right, the first orbital in a clockwise direction, we're going to put the shaded part in where we're going to make the new sigma bond, right? So what we want to do is get the shaded part to go in to also make that constructive overlap in the new sigma bond. So we're going to have to rotate that p orbital in a counterclockwise direction, right? Since we're rotating them in opposite directions, this is called disrotatory, right? So this is a disrotatory ring closing reaction, right? And if we draw the result just focusing on that sigma bond, we can see that we have constructive overlap, right? This is our new sigma bond, right? Those orbitals will rehybridize and become hybrid orbitals, not p orbitals. And now we need to think about what happens with the methyl groups, right? So if this one rotates clockwise, the methyl group ends up pointing up. And here, if the p orbital rotates counterclockwise, the methyl group will also be pointing up, right? And that corresponds with that product that we drew there, all right? So the molecular orbital theory accurately predicts what we get from running this experiment, right? That we get the cis dimethyl compound from this disrotatory ring closure, right? And that's the key, disrotatory. Right now, if we look at the photochemical reaction, right? Photochemical, we're going to be looking at psi4, right? And again, if we go up here to psi4, we're going to have 3 nodes. Okay, so we can draw what that's going to look like. And if we have 3 nodes, we're definitely going to have one in the middle, right? And then we can have one, the first bond and the last bond. So that it looks like that, right? Again, just make the nodes symmetrical and you'll be all set, right? And again, we have the methyl groups pointing out to the side. And now if we want to do this overlap, if we rotate that orbital in the clockwise direction, to get the overlap we want, we're going to have to rotate the other orbital in the same direction, right? So again, we're doing this sort of motion. This is conrotatory. The two orbitals are rotating in the same direction, right? So this is a conrotatory ring closing reaction. And if we draw out the resulting new sigma bond, we have the overlap that we want, all right, that constructive overlap that we need. And if we look at where the methyl groups are, methyl group on the left is pointing up. The methyl group on the right ends up pointing down. So we can see in this reaction, we end up with the methyl groups trans. Right, whereas over here, we had cis methyl groups. Right, and the final point is that we can draw our curved arrows up here, right, for this reaction. And you'll note that the curved arrows look identical whether we do it thermally or photochemically. The only way we can understand and predict what's happening with the stereochemistry is to look at these molecular orbital pictures, right? That's the only way that we can say, yes, when we do this reaction with hexatriene, we're going to do a ground state reaction that will, using the molecular orbital picture, predict that we're going to get the cis compound. And if we do it photochemically, because we're in a different highest occupied molecular orbital, we're going to get the trans. Right? So this is the strategy we're going to use for looking at all electrocyclic reactions, whether they be 6 pi as in this case, or 4 pi or 8 pi and so on. All right? So hopefully this will help as you think about the problems you're working on for homework.